Now second example, give an example of a relation which is transitive but neither reflection nor symmetric. So in the example, first of all consider any one non-empty set. A equal to set of elements A comma B comma C. Here elements A comma B comma C belongs to set of all real numbers. But here find the relation is only transitive. So R equal to set of all. Yes, what is the transitive condition? A comma B belongs to R and B comma C belongs to R implies that ordered pair A comma C belongs to R. This is the transitive condition. So first, using the first two elements, write the one ordered pair. Use the first two elements. Ordered pair is A comma B. Using the last two elements, write the ordered pair is B comma C. So here A comma B belongs to R, B comma C belongs to R, implies that ordered pair A comma C belongs to R. So this indicates this relation is a transitive relation. This relation is a transitive relation. But this relation is not a reflexive relation, because the reason is this example R is not a reflexive, because the reason is A set containing three elements. To take all the three elements double heads, A set first element is A double it is A comma A set second element is B double it is B comma B, third element is C double it is C comma C. All the three elements double heads are not belongs to this relation. That's why this relation is not a reflexive relation. Next, find this relation is not symmetric. Now take this relation, take any one pair. For example, suppose take second pair. This relation is R is not symmetric. Because the reason is as B comma C belongs to R implies that symmetry means B comma C inverse must be in the relation, then only this relation is symmetric. Now take the B comma C inverse. B comma C inverse is C comma B. C comma B not in the relation. C comma B is not belongs to R. So this relation is not symmetric. Or take this relation, any other pairs, A comma B in the relation, A comma B inverse, B comma A not in the relation. So this is not symmetric. Suppose take last pair, A comma C in the relation, A comma C inverse, C comma A is not in the relation. So this is not the symmetric relation. So this relation is only transitive, but neither reflexive nor symmetric. Now take a third example, reflexive and symmetric. Give an example of a relation which is the reflexive and symmetric, but not transitive, reflexive and symmetric, but not transitive. We can take in general three elements or take any three real numbers. For example, let A equal to in general three real numbers or take in general ABC or take any three real numbers. Now take the in general elements are ABC, or in place of ABC take any three real numbers. So what is the required example? Relation is reflexive and symmetric. Now take the first reflexive relation, R equal to. First of all, relation is reflexive. A set containing three elements. Now take all the three elements double heads. A element double it is A comma A. Second A set second element is B double it is B comma B. A set third element is C double it is C comma C. Here three elements double heads in the relation. So this relation is a reflexive relation. Next, and symmetric relation. In the set, using the first two elements, write the one ordered pair. First two elements, ordered pair is A comma B, but relation is symmetric. Means take this A comma B inverse. Ordered pair A comma B inverse is B comma A. Now take one more pair. Using the last two elements, this A set, using the last two elements, write the one ordered pair. Ordered pair is B comma C. B comma C in the relation, but symmetric, this inverse must be in the relation. So take this B comma C inverse is C comma B. So this relation is first of all reflexive, because A set all the three elements doublets are in the relation. Next, last four elements, last four pairs indicates relation is symmetric, because last four pairs indicates relation is symmetric. What is the reason here? A comma B in the relation, A comma B inverse, B comma A also in the relation. Next, B comma C in the relation, B comma C inverse, C comma B also in the relation. So this relation is reflexive and symmetric, but not transitive relation, because the reason is this relation is not transitive. R is not, relation is not transitive, relation is not transitive relation, because the reason is here A comma B belongs to R. This A comma B belongs to R, and this B comma C belongs to R, and B comma C belongs to, and B comma C belongs to R. This implies that AB belongs to R, B comma C belongs to R. This implies that ordered pair A comma C. Now this ordered pair A comma C is not in the relation. This ordered pair A comma C is not in the relation. So this relation is reflexive. This relation is reflexive and symmetric, but this relation is not transitive relation. Okay. Now come to the third example. All these are the important examples, theory as well as CET. Now take third example. Next, third example. Give an example of a relation which is reflexive and transitive, which is reflexive and transitive, but not symmetric, Now take the example. First take any one non-empty set. Let A equal to, take the in general non-empty set is set of elements A comma B comma C. Now capital R equal to, find the relation. That relation is reflexive and transitive, but not symmetric. Okay. First of all, find the reflexive relation. A set containing three elements. Now take all the three elements doublets in the relation. First element is A doublet is A comma A. Second element is B doublet is B comma B. Third element is C doublet is C comma C. This indicates relation is reflexive relation. Next, find the transitive. In the transitive condition is A comma B belongs to R, B comma C belongs to R, implies that A comma C belongs to R. Then the relation is transitive. Means this relation is reflexive and transitive, but not symmetric. This relation is reflexive and transitive, but not symmetric, because the reason is this relation is not symmetric. symmetric, because the reason is as what is the condition for symmetric? If relation set all the pairs inverse also lies in the relation, then only that relation is symmetric, otherwise not symmetric. Now take a relation set, first three pairs are doublets inverse definite lies in the inverse. Sorry, this relation means when take doublets inverse, again we get doublet, means first three indicates relation is symmetric. Now take last three pairs, anyone, last three pairs, suppose take first one, as A comma B belongs to R, this implies that. To find the symmetric, take this A comma B inverse. A comma B inverse is ordered pair B comma A. Now find the B comma A belongs to R or not belongs to R. This B comma A not in the relation, ordered pair B comma A not belongs to R. So this relation is not a symmetric relation. Okay, that's so this is only reflexive and transitive, but not the symmetric. Now take the fourth example. Give an example of a relation which is reflexive and transitive. So this is completed. Fourth, reflexive and symmetric. Reflexive and symmetric. Reflexive and symmetric. Reflexive and symmetric, but not transitive. Reflexive and symmetric, but not transitive. But not transitive. Okay. Now this example. Now reflexive relation. This is also completed. Third one. Now this is the fourth example. Means take the last fifth example. Okay. Now fifth example, find the relation. Give an example of a relation. This is already completed. Give an example of a relation which is symmetric, and transitive, but not reflexive. To write this example, first take any one non-empty set. A equal to set of elements A comma B comma C. Now R equal to find the relation set. First of all, that relation is symmetric relation. Using the first two elements, write the one pair. Ordered pair is A comma B, but relation is symmetric. Mistake this ordered pair A comma B inverse. Ordered pair A comma B inverse is ordered pair B comma A. So this indicates relation is symmetric. But find the relation is symmetric and transitive. Know that transitive condition is two pairs must be in the relation. But the first pair second element, second pair first element must be same. Now in the relation, first two pairs, first pair second element, second pair first element is same. So this A comma B belongs to R, B comma, this A element is considered C, B comma C belongs to R, implies that confirm A comma C belongs to R or not belongs to R. What is A comma C? A is A. In place of C, C element is A. C element is A. So this relation is symmetric as well as transitive, because this relation set every pair inverse also lies in the relation. So first of all, this relation is symmetric because A comma B belongs to R, inverse B comma A also belongs to R. A comma A is doublet inverse is again we get this A comma A doublet. So this relation is first of all symmetric. and this relation also indicates a transitive relation because here a comma b belongs to R, next b comma this a element consider a, b comma c belongs to R, implies that a comma c, in place of a is a comma, in place c is a, in place of c is a comma a in the relation. So this relation is symmetric and transitive but not reflexive. This relation is symmetric and transitive relation, but this relation is not a reflexive relation because the reason is R is relation is not reflexive, relation is not reflexive because this relation set only first element doublet lies in the relation. This A set take last two elements doublets, last element is B, B doublet is B comma B, next A set third element is C, B comma B is not belongs to R, A set last element is C, C doublet is C comma C, this also not belongs to R, means A set last two elements doublets are not belongs to this relation. That's why this relation is not reflexive because only first element doublet lies in the relation, last two elements doublets are not lies in the relation. So this relation is only symmetric and transitive, but not reflexive. Okay. Now take the remaining problems on relations. All these are the important examples. To solve the problems on relations, first of all, we should remember all the types of relations. Otherwise, we cannot solve the problems on relations. So take the remaining problems on relations. Next one is fifth example. Determine the relation capital R. Next example, determine the relation capital R in the set capital N, of natural numbers, capital N of natural numbers defined as capital R equal to set of all ordered pair x comma y such that y equal to x plus 5, under the condition is x is less than 4, is reflexive symmetric and transitive, Now take the solution. This solution, first write the non-empty set. Here given that set is capital N. Capital N indicates set of all natural numbers. So in the example given that A equal to non-empty set is capital N, A equal to capital N indicates set of all natural numbers, A set. On this A set, this relation is defined. So R equal to, using this A set, first of all find the relation set. Given that any pair in the relation, only when pair second element is equal to first element plus 5. So given that y equal to x plus 5. Using this condition, find the relation set. But your condition is x is less than 4. All the values of x are less than 4. x less than 4, x equal to 1, 1 is less than 4. Put this x equal to 1 in this y equal to x plus 5. So y equal to x is 1, 1 plus 5 is 6. Next x equal to 2 because 2 is less than 4 and 2 is the natural number. Next put this x equal to 2, y equal to 7. Next x equal to 3. 3 is less than 4 and 3 belongs to natural number. Therefore y equal to, it in place of x equal to 3, 3 plus 5 is 8, y equal to 8. Therefore relation R equal to set of all ordered pair x comma y. X is 1, y is 6. Ordered pair 1 comma 6. Next ordered pair 2 comma 7. Ordered pair 2 comma 7. Next ordered pair 3 comma 8. Ordered pair 3 comma 8. Now find this relation is reflexive, symmetric and transitive. So first of all find the one by one. First take a reflexive relation. To find the reflexive, what is the condition? A set containing natural numbers. We cannot take easily all the doublets of natural numbers. So take natural numbers any one doublet, because suppose any one doublet not in the relation, then also relation is not reflexive. So this first one is take reflexive relation as a set natural number. Take natural number, first element is 1. Now take one doublet 1 comma 1. 1 comma 1 is not belongs to this relation. That's why this relation is not reflexive, because if any one doublet not lies in the relation, then also relation is not reflexive. Here A set containing natural numbers, we cannot take all the natural numbers doublets. That's why take A set first element doublet is 1 comma 1. 1 comma 1 is not in the relation, so relation is not reflexive. Therefore R is not, relation is not reflexive. R is not reflexive relation. Okay. Now take second one is symmetric. Next symmetric. Symmetric. What is the symmetric condition? If relation set all the pairs inverse also lies in the relation, then only relation is symmetric. As now take relation set any one pair. Suppose take second as ordered pair 2 comma 7 belongs to R. This implies that. Now take 2 comma 7 inverse. Ordered pair 2 comma 7 inverse is ordered pair 7 comma 2. 7 comma 2 is not lies in the relation. So this ordered pair is not belongs to relation. That's why this relation is not symmetric. Therefore R is relation is not symmetric. Relation is not symmetric. Or you take any other pair. Suppose ordered pair 3 comma 8. 3 comma 8 in the relation. 3 comma 8 inverse 8 comma 3. 8 comma 3 is not in the relation. Means the relation is not symmetric. So in short, symmetric means if relation all the pairs inverse also lies in the relation, then only that relation is symmetric, otherwise not symmetric. Now take next transitive relation. Third one is transitive relation. In the transitive, what is the condition? Two pairs must be in the relation. Okay. So take first pair in the relation. These three pairs, take any one pair. Suppose take 3 comma 8 as 3 comma 8 belongs to R, 3 comma 8 belongs to R, and so what is the transitive condition? First pair second element, second pair first element must be same. Now this 3 comma 8 belongs to R, first pair second element is 8. That's why second pair first element must be 8 comma. 3 comma 8 belongs to R, next 8 comma. 8 comma, no any pair lies in the relation. Means this relation only this 3 comma 8 is only A comma B belongs to R, only 3 comma 8 belongs to relation. Another 8 comma no any pair in the relation. Means in the relation only one pair in the relation, 3 comma 8 in the relation. If only A comma B belongs to relation, then that relation is said to be transitive relation, because in this case transitivity is not contradict, because we know that if two pairs in the relation, third one is not in the relation, then only we can say relation is not transitive. But now this relation only A comma B belongs to R. If only one pair belongs to R, then directly we can say this relation is R is relation is transitive relation. Relation is transitive relation, because here in this case transitivity is not contradicted. That's why this relation is transitive. So here remember, if only one pair A comma B means only one pair A comma B belongs to this relation. Here what we take A comma B? Here we take A comma B means 3 comma 8. So take in general, if A comma B belongs to R, then directly you can say relation is transitive, because in this case transitivity is not contradicted, because in this case the reason is because in this case transitivity is not transitivity is not contradicted. That's why relation is relation. This show not relation because this order indicates relation. So take sixth example. Next one is sixth. Show that relation capital R in the set. Next example. Show that the relation capital R set of elements 1, 2, 3 given by R equal capital R equal to set of pair 1, 1 ordered pair 2, 2 ordered pair 3, 3 next pair is 1, 2 ordered pair is 2, 3. This is the relation defined on this A set. Is reflexive, but neither symmetric nor transitive, but neither symmetric nor transitive, neither symmetric nor transitive. Now take this solution. Now first of all take a non-empty set. In the example given that this is the non-empty set. So take let A equal to non-empty set is this set of elements 1, 2, 3. Next find this relation defined on this A set is reflexive but neither symmetric nor transitive. So what is the relation? This is the relation. First of all find the reflexive relation. First reflexive A set containing 3 elements. Now take all the 3 elements doublets. First element is 1 doublet is 1, 1. Second element is 2 doublet is 2, 2. Next element is 3 doublet is 3, 3. So all the 3 elements doublets are belongs to relation. So this relation is reflexive relation. All these pairs are belongs to relation. So this relation is reflexive. Therefore R is relation is reflexive. R is reflexive relation. Next now take the symmetry relation. Second one find the symmetric. Next symmetric. Now relation set all the pairs. If all the pairs inverse lies in the relation, then only relation is symmetric, otherwise not symmetric. relation set, first three pairs are doublets. We know that doublets inverse also lies in the relation. So first three indicates symmetric. Now take last two, any one pair. Take last two, the second last pair. What is the pair 1, 2? Symmetric as ordered pair 1, 2, as ordered pair 1, 2 belongs to this relation. This implies that take this ordered pair inverse. Ordered pair 1, 2 inverse is 2, 1. Now this ordered pair 2, 1 is not lies in the relation. This ordered pair is not belongs to relation. So this relation is not symmetric. Therefore R is not symmetric. Therefore is not symmetric. Next find the transitive relation. Find this relation is transitive or not transitive. In the transitive, remember the condition. The two pairs must be in the relation. But in the two pairs, first pair second element, second pair first element must be same. In the last two pairs, first pair second element, second first element is same. So take last two as ordered pair 1, 2 belongs to R. And order to belongs to R. This first order pair to belongs to A, belongs to R. This A, B belongs to R. 2, 3 belongs to R. Implies that order pair A, C belongs to R. What is A, C? Is 1. C is 3. 1, 3. Ordered pair 1, 3. Ordered pair 1, 3 is not lies in the relation. So this ordered pair 1, 3 not R. Means relation is not transitive. Therefore R is a relation is not transitive. Relation is not transitive. Relation is only neither symmetric nor transitive. Okay. Now remaining examples. 6 examples are completed. Take remaining examples. Only remember the types of relations. Remember all the definitions. Next, seventh example. In the seventh, the first, the relation capital R. Show that relation capital R. Show that the relation capital R in the set capital A equal to set of elements 1, 2, 3, 4, 5. Given of all order A, B of A minus E is modulus of minus E is if the relation defined on this A set is an equivalence relation. Is an equivalence relation. We know that what is the definition of equivalence relation? If relation is reflexive and transitive, then only that relation is equivalence relation. Means this example show that this relation satisfies reflexive, symmetric and transitive. Suppose this relation not satisfies anyone, then that relation is not equivalence relation. Means prove that this relation satisfies reflexive, symmetric and transitive. Now take one by one. Now take given relation, given that R equal to set of all ordered pair A, B such that modulus of A minus B is even. Now this is a relation. Find the one by one. Now first take reflexive relation. First reflexive relation. In the reflexive relation, here take in general, not relation set. Now we have to prove the in general reflexive relation. First write the reflexive definition. In the reflexive, now take for every, given that the relation containing elements in the form of A and B. These two elements, take any one element. Now take the first element. For every, this A element is belongs to this given non-empty set. As definition of reflexive is for every A element is related to itself. This is the definition of reflexive relation. In the in general examples, in the solution of this type examples, first of all, we have to write the definition of reflection relation. So after that, to find this is reflexive or not reflexive, apply this relation on this ordered pair. This implies that apply the relation on this pair. So what is the relation? Any ordered pair in the relation only when modulus of pair first element minus pair second element is even number. So any pair in the relation means modulus of pair first element minus pair second element is equal to modulus of a minus a, modulus is 0. But this is a even number, 0 is even number. Means modulus of pair element minus second element is 0, 0 is even. Now this is the true. This is means relation is reflection. Therefore, R is reflection. Therefore, R show relation. Now once again, examples. To find the reflection relation, first of all, write a definition is given that the elements in the, so take first element for your element non-empty. Definition is element is related to itself. Now this is the definition of reflection relation. To find this is reflexive or not reflexive, apply this relation on this ordered pair. Given that any pair in the relation only when modulus of pair first element minus second element is equal. So take this pair in the relation means modulus of ordered pair first element minus second element. Modulus of a minus a is 0 and we know that 0 is even. This is the true. This indicates relation is reflexive relation. R is reflexive means this relation is reflexive relation. Next, now see the transitive relation. Next relation is transitive relation. Before the transitive, second relation is symmetric relation. The symmetric. Define the symmetric relation. Now consider two elements, but in general two elements. Now for every this relation set, given that elements in the form of A and B. So first element is A, second element is B. Take for all A comma B belongs to non-empty set A. In the symmetric, now take the two elements belongs to non-empty set. As in the symmetric, one more condition is A comma B must be in the relation. So using the two elements, write the ordered pair as the ordered pair A comma B belongs to R. This implies that already given that ordered pair A comma belongs to R means modulus of minus B is even. Ordered pair A comma B belongs to R means modulus of A minus B is even. Modulus of A minus B is 1 because already given that ordered pair A comma B belongs to R means modulus of A minus B is even. Okay. So next, in the symmetric, if A comma B belongs to R, next find this inverse also belongs to R, then only this is symmetry, otherwise not the symmetric. Next, now take modulus of to find this symmetry. Take this A minus B minus sign common. In the A minus B minus common in the bracket is B minus A. Modulus of minus B minus A is even number is even. And this implies that of B minus A. And this last is even as it is. Means if modulus of minus of B minus A is even, implies that modulus of B minus A is also. For example, now take any two element non-empty set. But what is the condition? Mod A minus B must be even number. Now take the two elements belongs to elements set. Mod A minus B is even. 1. A equal to 1. Next 2, 3. Find out A minus B is even. Modulus of A minus B equal to modulus of A minus 1 minus minus plus minus 2 is plus 2. So modulus of minus even number. Next take modulus of B minus A. This is B minus A. Now this 3 minus 1 is 2. Modulus of 2 is equal to 2. Means if mod A minus B is even number, mod B minus A also even number. So this mod A minus B is even number implies that mod B minus A is even number. And this A, second element is A. Ordered pair B comma A belongs to R. That's the relation is symmetric. Therefore, R is symmetric. relation is symmetric relation. Last one. Okay.